Hello, and welcome to our continued discussion of curves. Let's fix a curve gamma that goes from the closed bounded interval a to b in the reals into the complex plane. At the end of our last video, we remarked on the notion that curves have a kind of orientation. They start at one point and go to another point. What if we flip the direction in which a curve moves? Say we start at the terminal point and go back to the initial point. There is a way to make this algebraically precise in terms of the definition of a curve, and it is called the reverse of the curve. So the reverse of gamma is the curve gamma minus of t, which we define to be gamma of a plus b minus t for t between a and b. So what does this do? Ideally, gamma minus should start at gamma of b and take you back to gamma of a. Let me do the calculation. Gamma minus of a is gamma of a plus b minus a, which is gamma of b. And gamma minus of b is gamma of a plus b minus b, which is gamma of a. So, as we desired, this flips the initial and terminal points of gamma. The initial point of gamma minus of a, is now gamma of b, which is the terminal point of gamma. And conversely, the terminal point of gamma minus, which is gamma minus of b, is gamma of a, which is the initial point of gamma. So here was a line segment that we saw in the previous video. We go from z0 to z1 with gamma, and then the reverse will take us from z1 to z0. Now, suppose we have two curves, and the terminal point of one curve is the initial point of the other. There's a natural way to join these two curves together. So a little more precisely, we'll take a curve gamma 1 defined on the interval a to b, and a curve gamma 2 defined on the interval c to d, and gamma 1 of b is equal to gamma 2 of c. So the terminal point of gamma 1 is the initial point of gamma 2. Let's draw this. So here's our complex plane. Here's our first curve. Its initial point is gamma 1 of a. Its terminal point is gamma 1 of b. Here's our second curve. The initial point is gamma 2 of c, the terminal point is gamma 2 of d, and we note that gamma 2 of c is equal to gamma 1 of b. So how can we define a curve that sort of composes or sticks gamma 1 and gamma 2 together? We need a somewhat dreadful piecewise formula. So the composition of gamma 1 and gamma 2 is the curve gamma 1 composed with gamma 2. I'm using here the symbol O plus in LaTeX for gamma 1, O plus gamma 2. It's defined on the interval a to b plus d minus c, and it's a piecewise function. It's gamma 1 of t for t between a and b, and gamma 2 of t minus b plus c for t between b and b plus d minus c. And this curve will have the image gamma 1 up until t equals b, and then gamma 2 onwards to the end of the curve gamma 2. It's also a rather dreadful formula, and I doubt I will ever ask you to actually work with it in any calculations, but it's just good to know that we can make precise what it means to join two curves together. And here are some pictures that I think illustrate the situation a little better. We start out with gamma 1 defined on this interval a to b, and then we have gamma 2 defined on some other interval c to d. And we put gamma 1 and gamma 2 together by defining it on an interval that starts at a and goes up to b plus d minus c. So it's sort of like we slide the intervals a to b and then c to d together into one big bad interval, a to b plus d minus c. As an example, let's find four curves, gamma 1, gamma 2, gamma 3, and gamma 4, such that the image of their composition, gamma 1 composed with gamma 2, composed with gamma 3, composed with gamma 4, is the curve below. Now, a couple of things about how I like to draw curves. First, if there's an obvious initial and terminal point to a curve, I will use an arrow to indicate that. So look at the upper arc here that starts at r, passes through IR, and goes to minus r. I have arrows pointing on the arc from r to IR, and then from IR to minus r, and that tells you should be tracing out this arc in the counterclockwise fashion that we know and love from trigonometry. Next, from time to time, I will draw curves, part of which are line segments that overlap with some of the coordinate axes. So look at that piece from epsilon to r. I've drawn it a little thicker and in a more lightly shaded blue. I'll do that just to indicate that I do have a portion of the curve running along the axis, because I don't want a thinner curve to get overshadowed by the axis and have you confused with distinguishing between axis and curve. So it's thicker there just to indicate that the curve is running along the axis. Now, it looks like I have 4 pieces in this curve, 2 line segments and 2 circles. So let's use that in finding the 4 curves gamma. So my first piece will be the line segment from epsilon to r, and that's parameterized by 1 minus t times epsilon plus t times r for t between 0 and 1. And whenever I give a parameterization of a curve, I should have some formula for it, and I should have the domain. I need to know what closed bounded interval t lives in. Next, I'll do the semicircular arc from r to minus r in the upper half plane with the imaginary part of z greater than 0. And that's going to pass through IR. So that parameterization will be r e to the it for t between 0 and pi, because this is part of the circle of radius r centered at the origin. I'll do the line segment from minus r to minus epsilon. That's easy. That's 1 minus t times minus r plus t times minus epsilon for t again between 0 and 1. And last, I need to do the semicircular arc from minus epsilon to epsilon. And here it looks like the reverse of the usual counterclockwise orientation, right? Because I'm starting at minus epsilon and going over to positive epsilon. So the right parameterization here is epsilon times e to the I pi minus t for t between 0 and pi. How would I get that? Well, the more familiar curve would be epsilon times e to the it that would go from 0 to pi. That would start at epsilon, pass through I epsilon, and go to minus epsilon. This familiar curve is the reverse of the one I have, so I just use the formula for my reverse curve here to get epsilon times e to the I pi minus t.